You ever see this happen? An AI that seems like an absolute genius in the lab suddenly just falls apart when it hits the real world? We see these incredibly powerful models, right? But they have this hidden weakness. They can be surprisingly fragile when they encounter something new. Today, we're going to dive right into that paradox.
So that's the big question, isn't it? Why do these brilliant AIs fail in new situations? You know, a self-driving car that's trained on sunny California roads might just completely freeze up in a snowy Toronto winter. Or a medical AI trained on one hospital's x-rays could totally misdiagnose images from another. So why does this happen? Well, the answer comes down to a core concept in machine learning.
And that concept is called domain shift. Think of it this way. You train an AI to identify animals using thousands and thousands of color photographs. It gets really good at it. But then you show it a simple black and white sketch of a cat, and the AI, it's just confused. That's domain shift in a nutshell. It's that gap between the neat, tidy training world and the messy real world.
Now, here's the thing. This isn't some one-time problem you can just patch and forget about. The real world is always changing, right? It's creating this continuous, dynamic challenge for our AI systems. This is what we're calling the AI's real-world blind spot. Researchers, of course, have a name for this massive challenge, UCDSL. That stands for Unsupervised Continual Domain Shift Learning. So let's just break that down really quick. Unsupervised means the AI is seeing new data without any labels telling it what's what. Continual means the environment is always changing. And the goal is to get the AI to learn and adapt on the fly without throwing out all the valuable knowledge it's already picked up.
And what you've got to understand is that UCDSL is this really tough balancing act between three competing goals. The AI has to get good at the new environment it's in right now. It also has to get good at predicting what future environments might look like. And this is the really critical part, it can't forget what it learned from all the past environments. Juggling these three things at once is what makes this problem so incredibly hard.
So how have people tried to solve this? Well, for a long time, the main approach was to build one giant master model that could handle everything. But as we're about to see, this one-size-fits-all strategy has a really fundamental flaw. The logic behind it was pretty straightforward. If all the different domains are the problem, hey, let's just teach the AI to ignore the differences. The goal was to find what's called a domain invariant representation, sort of the core essence of the data that's true whether you're looking at a photo, a sketch, or a cartoon. It's kind of like trying to create one universal key that can open every single lock in the world. But here's the catch, and this quote from the source paper just nails it. By forcing the model to ignore all those domain-specific details, you're actually throwing away super valuable information. Think about it. The unique texture of a painting, the sharp lines of a sketch, those details are often crucial for making an accurate guess. You end up limiting the model's ability to tell things apart. So you see the mismatch here, right? The goal was this universal master tool, but trying to build it created this hidden flaw, a huge adaptivity gap. The master tool became a jack of all trades, but a master of none. It was actually suboptimal on every single domain because it wasn't specialized for any of them.
And this brings us to the really cool part, the breakthrough proposed in this research. Instead of trying to force one tool to do everything, what if we built a smarter, more specialized toolkit instead?
The new idea is a total shift in thinking. Forget the master key. Instead, think of it like building a keychain. Every time the AI runs into a new type of lock, a new domain, it forges a brand new key specifically for that lock, and then just adds it to the collection. The technical name for this is multi-prototype learning, or MPL. A prototype here is basically that specialized tool, that unique key we were talking about. So MPL is the engine that builds the toolkit, creating a distinct, expert model for every new environment the AI sees.
The process itself is beautifully simple. First, the AI sees a new environment, let's say a bunch of cartoon images. Then it forges a new cartoon prototype that's specifically designed to understand cartoons. And this is the most important part. It adds this new tool to its toolkit without throwing away the old ones for photos and sketches. This is exactly how it avoids that catastrophic forgetting problem.
Okay, so building a great toolkit is half the battle. But you also need a skilled craftsperson who knows exactly which tool to use for the job, right? And that's where the second major innovation comes into play.
This master craftsperson is a component called the Bi-Level Graph Enhancer, or BIG for short.
Its entire job is to look at a new piece of data and intelligently select and combine the knowledge from all the different prototypes in the toolkit to make the smartest possible prediction.
So how does it pull that off? Well, BiG basically performs a two-level fact check on the data. It asks two very simple but very powerful questions to refine its understanding before it makes a final decision.
First up is the domain level check. Big asks, okay, what kind of world did this image come from? Is it a photo, a sketch, a piece of art? This helps it pick the right specialist tool from the toolkit. Then second is the category level check. Now it asks, all right, what does this thing actually look like? Does it have the features of a dog or a cat or a lion? By combining the answers to both of those questions, it makes a much more robust and accurate prediction.
Okay, that all sounds fantastic on paper, but does it actually work? Let's take a look at the results. The researchers visualized the data to see how well these different methods could actually organize it.
So visualizations from the older one-size-fits-all methods show us exactly why they fail. I mean, look at this, it's a complete mess. The different categories, represented by the colors, are all jumbled up and bleeding into each other. There are no clear boundaries. The model is just confused. It can't tell where one thing ends and another begins.
But then you look at the new multi-prototype approach and wow, the difference is just night and day. The model creates these tight, confident, clearly separated clusters for each category. They look like distinct little islands of color. It's the perfect visual proof that using specialized tools leads to a much smarter, more organized model.
And this improvement isn't just a pretty picture, it is quantifiable. The ablation study in the paper shows that just by switching from a single universal classifier to this new multi-prototype approach, they boosted overall performance by 2.1%. And that might not sound like a huge number, but in a field like this, every single percentage point is a really big deal.
So what does this all mean for the future? This research isn't just about a small performance bump. It's really pointing toward a fundamental shift in how we think about building AI that can actually learn and thrive out in the real world.
Let's just recap the three key breakthroughs here. First, it mathematically proves that embracing domain differences, instead of ignoring them, actually leads to better performance. Second, it gives us a practical method, that multi-prototype learning, to create a toolkit of specialized models. And third, it adds that intelligent fact checker, the bi-level graph enhancer, to make the final predictions way more reliable.
And this really leaves us with a final thought to chew on. You know, the old model of AI was all about obeying, just following a fixed set of rules it learned in a static, predictable environment. But as we move toward more autonomous systems, ones that have to operate in our messy, ever-changing world, well, maybe the goal shouldn't be perfect obedience, but continuous intelligent adaptation. Shouldn't we be building AIs that learn how to learn?